Let's look at some examples of linear functions, functions that can be written in the form mx plus b. Example, a car rental company charges $40 as a flat fixed fee plus 30 cents per mile. What is the cost function? This is a function of something. What's it a function of? The number of miles driven. So x should represent the miles driven. And we're interested in cost as a function of x. Okay, well, the cost is going to be $40 no matter what we do. So let's start with that. That's our fixed cost. And then we've got a cost that's per mile. When you see per anywhere in your problem, you're thinking that's a rate. That's like a slope. And in this case, it's 30 cents per mile. So I might have 30 times x, but let's make sure we're careful with the units here. The 40 is in dollars, and the 30 is in cents. So let me be very careful to get my decimal point in there. Say this is 0.30x plus 40, linear cost function. Let's try out our function if the car has been driven 300 miles. So if x equals 300, let's plug 300 in to our equation. So x is 300 plus 40, and I obtain $130 for the rental cost. What is the average rental cost per mile if the car has been driven 400 miles? So let's find the cost to drive 400 miles first. 0.30 times 400 plus 40 is 120 plus 40 is $160. Okay, that's not what this problem is asking for. It costs $160 to travel 400 miles. What's the average cost per mile? Average cost per mile is going to equal the cost of driving 400 miles divided by total number of miles, 400 miles. In other words, we're looking at $160 divided by 400 miles equals 40 cents per mile. Okay, you say, well, I thought it cost 30 cents per mile. That's true, but this includes the $40 fixed expense. And if you spread $40 over 400 miles, that's an extra 10 cents per mile. So this makes sense that it's costing 40 cents per mile. Here's another example of a linear function. We know the cost to produce a certain amount of cell phones, and we have the cost to produce a second amount of cell phones. And we can think of this as 2 points. I've got the point when x, what's x mean? X is the cell phones. And what's y? Y is the cost, the dollar amount. So I've got 1 point where x is 100 and y is 4,000. And I've got a second point where x is 200 and y is 6,000. Okay, so with these 2 points, I can find the slope. So let's summarize here. I've got 2 points, 100, 4,000, and a second point of 200, 6,000. And so assuming that this is a linear function, we can find its slope. That will be the change in the cost divided by the change in cell phones. Okay, so to produce an extra 100 cell phones cost an additional $2,000. In other words, it costs $20 per phone. Right, the units here are y over x. Y is in dollars, x is the number of phones. And so when we say the slope is 20 here, what we mean is $20 per phone. Okay, so what's the cost function? Well, all I have right now is the slope. What's the line that has this slope and goes through our points? I could use point slope form or a different equation if you like, but let me grab that first point. I know that y minus 4,000 is m times x minus x1, where x1 is 100. In other words, y is 20x minus 2,000 plus 4,000 is plus 2,000. Okay, so in answer to this first question, the cost function is $20 per phone times the number of phones plus $2,000. And if we look at the graph, the intercept is at 2,000, and when x is 100, the cost is 4,000, and when x is 200, the cost is 6,000. So here is this point, here's this point. We know the intercept, the slope here is 20, and so my line will look something like this. The fixed cost is what it costs to produce 0 phones, and you can see that right here. That's the y-intercept. It's right here. So fixed cost corresponds to the y-intercept. In this case, the cost to produce 0 phones is $2,000. You say, how is that possible? Well, I still have to turn on the lights in the factory and pay the janitor and all of these kinds of things before I ever produce a single phone. What's the slope mean? We already mentioned this in the equation, but it's cost per phone. And that's ignoring the fixed cost, ignoring this $2,000 y-intercept. $20 to produce an additional phone. What's it cost to produce 250? Well, I just want to plug in 250 for x, right? 250 is an x value. X represents the number of phones. So 20 times x is 250 plus 2,000, and we obtain $7,000. What's the average cost per item? The total cost was $7,000, and at a cost of $7,000, I produced 250 cell phones. So when we divide, I get $28 per phone. You say, I thought the cost per phone was $20. Well, that doesn't take into account the fixed cost. So here we're including the overhead of $2,000 and spreading that out per item. And so in this case, the cost per item to produce 250 cell phones comes out to $28 per phone. Of course, as I increase the number of phones produced, this averaged cost per item will decrease and get closer and closer to $20 as the $2,000 fixed cost becomes less and less significant per phone. So just to summarize linear cost functions, the cost is given by mx plus b, and the slope, the m, is what we might call the marginal cost, or this is sometimes known as the direct cost per item. It's the cost per item ignoring the fixed cost, which is what we call B. B is the fixed cost. M times X is sometimes known as the variable cost. And so if we write C of X is mx plus B, we could also say that as variable cost plus fixed cost. And as we saw in our examples, the average cost per item is the total cost for X items divided by the number of items. Let's look at a depreciation example. Suppose I have an automobile with this initial value and it decreases to being worth only $8,000 at the end of 5 years, and we assume this depreciation is linear. How can we describe this in terms of X, where X is the number of years? We need to find the slope, and the slope is given by the fact that my price has gone from currently $8,000. It used to be $25,000, so the price has gone down $17,000 in the course of 5 years. Okay, in other words, the car has depreciated $17,000 over the course of 5 years, which means if the model is linear, it's depreciated $3,400 per year. Okay, so that's the slope. What's the value function then? Well, we know the slope and we know the intercept. The car was initially worth $25,000. That's my B. And we know the value goes down $3,400 per year, where year is given by X. So here's my value function. If we draw the graph, I'm up here somewhere at 25,000, and we're depreciating over the course of 5 years. And let's see, if this is 5, then I guess at the end of 5 years I'm down here at $8,000. What's the slope represent? This 3,400 is dollars per year. It's negative, and it's the annual depreciation, the change in value per year, annual. What's the value at the end of 4 years? Remember, X represents time, represents years, so I'm plugging in X equals 4 into my equation. Negative 3,400 times 4 plus 25,000, and I get that the car is worth $11,400 at the end of 4 years. Now, of course, this model is going to have some problems, especially if we ask it to determine the value of the car, say in 10 years, and it tells us the car is worth negative $9,000. A more realistic model of depreciation might be, well, the price really drops off when you go off the lot, and then maybe it doesn't decrease quite so much. And then as the car gets old and starts to break down, it becomes worth less and less. But of course, it's always worth, well, maybe something to somebody. And so the linear model may work on a small scale, but there may be better mathematical models to explain depreciation. So just to summarize, if we assume the depreciation is linear, if we assume that it is a straight line, then what did our equation look like? The y-intercept was the initial price, the purchase price. And the annual depreciation is our slope. And we want to make sure here that that's a negative quantity. X is the number of years. And so our equation looks like this. Now, sometimes people talk about the salvage value of an item, and that's if it has any value at the end of its useful life. And so the net cost of having something is the purchase price, what you initially paid for it, minus what it's worth at the end of its useful life. So the difference between purchase price and salvage value. And how does net cost relate to annual depreciation? Annual depreciation is the ratio of the net cost to the number of years of its useful life.